But let's go ahead and talk about how this might work. All right, so let's build this thing. I, U. Where now the U is going to be that thing there. Now you'll see we're not quite done yet because there's going to be some massive expression that we have here, right? It's going to be, you're going to have your P, and then you're going to have this gamma I, 5I. This is the x derivative on it, squared, plus Q, sum, gamma I, 5I, y, derivative squared, minus R, gamma I, phi I, squared, plus 2f, gamma I, phi I. Okay, so that's that first term there. Then you have your boundary conditions, plus on the boundary, G1. Don't forget my G1. Okay. So you see, big old mess. Where's my G1? I got a G1 up there. G1. Okay. All right. There it is. Not so bad. Okay, now what do you do? So you have everything there. You have it all expanded. And how do you pick out these variables, these gamma i's that you have all over the place, and these weightings that you want to do? What we know is that ultimately this integral had to what? Minimize something. You've picked this form of solution. What you've got left over, in fact, the a's and the, so let's come back over here. Your elements A, B, C are going to be used just to do a fitting to your neighbors. Right? How this is going to be all consistent, right? So these guys, remember, you have neighbors on every side, and you have to make yourself fit to all these neighbors. So it's going to give you some kind of fitting there. But in addition to that, you have the PDE that's going to carry information that has to satisfy that equation. And we want this thing to be minimized with respect to every single one of those gamma i's. Okay? See where I'm going with this, right? Now I'm going to take the derivative of this whole thing with respect to gamma I. It's not that hard, really. I mean, like gamma I appears here. You got to square this out. It's squared, and fine. I could do it. I could do it. I could do it. It's not like it's that hard. Just it's kind of a big, complicated mess. Then I've got to set it to equal 0. So what I'd like to do for you is write down the answer. I carry some of the calculus through here. Okay, it's in the notes a little bit. Even there, I kind of just give you the highlights. I don't even know what to call their highlights. Checkpoints. I call them checkpoints. All right, I give you checkpoints to check on. At the end of the day, this, AX equal to B. Let's construct A. Let's construct what the X is and what the B's are. Okay? So you do this. You do it for every single one of those variables. You get a bunch of constraints, which then give you an AX equal to B to solve, to meet those constraints. Yeah?
The second integral is only on S2.
Yeah, I was noticing that. I was hoping nobody else would notice. I got to check that, what happened with S1. I might have done this just on assuming, I think I did for this example, I just said assume that the whole boundary is just S2, which is that generic form. And it said forget S1. I think that's what I did. I might even said that in the notes. But when I started writing, I thought, I don't have time to read in class. You guys can. You guys totally can sit there and tune out, check your email, online shop, whatever. Not me, I'm working. All right. But I got AX equal to B, and let's talk about how to construct A and X and B, and all I got to do is figure out how to construct these elements, those and what the unknowns are, and how I set this up, and then you just, once you have that, right, then it's trivial. You just do this in MATLAB, and you're done, right? That's pretty simple. The setup costs you a lot. Okay? So first of all, what are the things I'm actually trying to determine? Well, the things I don't know here are these gamma i's. Okay, so actually your x and by the way, I'm only going up to the nth component. From m plus 1 to m, I actually know what they are because they have to satisfy the boundary. Okay? This is, notice what I'm, so m plus 1, m plus 2, all the way to gamma m plus m, those are actually satisfying a boundary condition associated with that second piece there, so they get determined. Everything in the interior, that's what I'm trying to determine here. So I got this x, that's what I'm trying to get out of this ax equal to b solve. B will be a bunch of betas, and I'll tell you what the betas are. And then A will have, I'll write the matrix components of A as alpha ij. That's the component in the ith row, jth column. And let me just show you what the betas are. The beta j's are the following: minus after a bunch of work, here's what the betas are. So you integrate over your function f, which is your forcing, times your elements, which are the phi ij's, which are the simplex elements, and you have a contribution from your boundary term, minus this also is a contribution from your boundary term, the alpha ij, which I'm going to give you in a moment, weighted times all the sum of the elements around the boundary that you already know. Okay? Remember when we did in class when we imposed boundary conditions for homework 2, right? If we had boundaries, they came back. If we knew what the boundaries are, they actually came back in. They could come back in into the right-hand side. That's what happens here. I know what the boundaries are. They come back into the right-hand side to force the system on the interior points. Now the alpha ij P, phi of I, x, phi of j, x, plus q, phi of I, y, phi of j, y, minus r, phi I, phi j, and that's that piece, plus integral over S2, ds, g1, phi I, phi j. Those are my matrix elements. Okay? So you can see it's pretty costly to construct this, right? I gotta evaluate all these things. I gotta actually go in there and do these integrals, and both in the interior and the boundary, and this will give me my alpha ij, which care about neighboring elements, phi I, phi j. For instance, you know, I'm taking the x derivative of 1 plus y derivative of 1. And if I'm on the diagonal, then this becomes phi I x squared, for instance. So, all right. So, I mean, look, it's algorithmic. Let's not kid ourselves here, right? I mean, ultimately, at the end of the day, there's no magic here, right? This is just a big algebra problem, and that you better do some pretty good bookkeeping on. And if you mess up one little bookkeeping spot, right? You're toast. So here, you just want to make sure you got everything right. But at the end of the day, it's just a formula. You program this up. Computer, do a loop. Go through. Compute every matrix element. I got ax equals b. I can backslash it. I'm done. Right? Okay? So that's what you would actually do. And then, after you do all this solution, I mean, it's more complicated than that, right? I mean, you got this. And remember, your solution, you assume, was on all this thing here was that you assumed that your solutions were something like this, right? Let's talk about plotting this thing. Right? When we have solved things before, everything was beautifully arranged by design. We made it on a grid, and the grid was perfect, and we just reshaped it, did some stuff, and then we want to plot. We say p-color it. Now, you've solved this thing. And you got all these things. You solve this big ax would be to get this. You have this. Now you have all this stuff. Now, how do I plot this? Now, you got to tell it, oh, well, I got to go through and tell it where every single little patch is. Well, it's not just P color. It's like, well, this patch lives here, and then that one lives here, and that one lives here. So plot that on this, 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 this. Even plotting this thing is a painful process. Okay? It's not that big a deal. It's management of information, right? At the end of the day, right? Just where everything go? So it's not that big a deal. On the other hand, if you don't have to write that, fantastic. Okay? Compare this to what we did. We saw the full 2D advection diffusion equation in class, right? Spectrally, right? We spent, what, 35 minutes? Wrote the whole thing out. And if you actually look at the number of lines of code, less than 20. 20 lines of code, I can solve a full 2D problem, run it in class, works beautifully, watch this vortex go. You cannot do that kind of programming with this, right? So even with MATLAB, there's no shortcuts to doing this crap. So this is why the popularity of ANSYS, PD Toolbox, Console, like all these programs, because they do it all for you. This is all just management of information for you, and that's actually what we're going to use. Okay? So I'm going to leave you with that. I think it's important that you know what's underneath this finite element technique. And hopefully, even just seeing this, it becomes pretty clear why toolboxes become so important for your life. If you're going to do something, right, you don't necessarily say, well, can I just write my own finite element code? Yeah, you can, if you want. How much time is going to cost you? A lot. And you have to make sure you don't get any single bug. How many of you have learned how to debug, right? I mean, you guys debug, right? How much does it cost you to track down that one little stupid thing? Now try to track something down in this, right? Okay? These professionals have done it. Let them give you a nice little piece of code. And that's what we're going to work on next week.